morning, everyone. Nice to meet you all. So today we're going to talk about number systems. But before that, I want to briefly just go through a few things from the survey that I sent out yesterday. People are asking, is it okay if I come into the class knowing nothing about hardware? And that's absolutely fine. The course is designed in a way that requires minimum prerequisites. I mean, in terms of EE, CS, or math, physics knowledge. And we'll try to make it as self-contained as possible. And another question is, I still don't quite understand things like quantization, CMOS, chip fabrication, and all those physics. Is that all right? And the answer is also yes. Lecture 1 is only for your curiosity. It's not going to appear on the exam, and we don't really have any technical questions about any of those. A few reminders. So please join our Slack workspace if you haven't. That's where we will make all the communication happen and make announcements. And here's a link you can use. It's also on our Canvas website. For the workbook, yesterday's workbook is due tomorrow before lecture. So every weekday workbook is due in 2 days. And today's workbook will be due on Thursday. So again, another 2 days. Discussion section starts tomorrow, where the TA will try to help you, go through some of these workbook questions and to guide you to, for problem solving or think more creatively. And office hours start today. I have office hours this afternoon, and your TA and tutor also have office hours today, tomorrow, and during weekdays until Thursday. So most of the office hours for Monday to Thursday will be in person. And the office hours on Friday, Saturday, or in the evenings, those office hours are more likely to be remote. So please check out the details on our course website and the course calendar. So here's our today's agenda. We're going to talk about positional number systems. The way, in general, we deal with decimal numbers, it is a positional weight system. By putting the same numeral at different positions, they actually have different magnitudes. And we're going to do some base conversion between, let's say, decimal, the one that we use in our daily life, and binary. And finally, we're going to see how to do addition, subtraction, some of these basic arithmetic operations in the binary world. So with that, I'm going to switch my presentation to the iPad so that I can make some annotations. Any questions, by the way, about the syllabus, the first lecture, or anything? Yes?
I wasn't here for the first lecture, so I was just wondering what we covered.
Just covered some introduction and the syllabus. And the lecture is also recorded, and you can see that on podcast and also on Canvas. Sorry guys, give me 1 second to screen sharing. Okay, now I think it's working. I need to switch it to the projecting. Perfect. So we're going to talk about number representations, right? Think about a very fundamental problem. How do we represent numbers? Again, I showed you these tally marks, right? Different cultures, different nations, different parts of the world using tally marks in different ways, but it's always the same idea, using one stroke to represent a single magnitude. If you want to represent the 5, they can be represented in a more compact way in this kind of a cubical shape. And that allows us to more easily visualize the overall magnitude of a number. We also have Roman numerals. And Roman numeral is an additive system, where every symbol has its own magnitude. And then the way you count up the magnitude of a full number will be just doing the addition of all the individual magnitudes. Even though there are some local relative rules, like you put an I before B, that means subtraction. But this is an additive and subtractive system. And what we care about in this class will be positional number systems. Again, decimal is a positional number. We just have 10 different numerals from 0 to 9. And when you put them at different positions, they have different magnitudes. So 1889, if you think about this number, right? So 9 is put at the rightmost position. So it has a positional weight of 1. So 9 really means 9 times 1. When we put 8 at the second position, it means 8 times 10. Right? So the positional weight is really 10. Can you see the color all right? Not quite. I'll use the yellow one. I think it's a little bit brighter. Is it better? All right. And then again, 8, the very same numeral, when we put that at the next position, has a positional weight of 100. And 1 next position, it's 1,000. right? But those are really just powers of 10, and 10 is the base that we're dealing with for these kind of Arabic numerals. You can generalize it into a formula for any positional number systems to represent the magnitude in terms of bases and individual numerals. So let me do a cut a little bit. I think my font is too big. So in general, you can represent numbers in any base. And again, you first need to define a set of numerals. And those numerals will form a numeral string. And each digit corresponds to a particular positional weight. Again, at the rightmost position, that would be positional weight of b to the 0, which is 1. Second position, b to the 1. Next position, b to the 2, etc. Right? And when you take the summation of all these products between numeral and the corresponding positional weights, that will be the magnitude of your full number. So if we compare this with what we saw earlier, right, that unary base 1 representation using tally marks and Roman numeral, I would say positional number has in general 3 benefits. For one thing, it's kind of intelligible. There are not many things you need to remember, right? Just need to remember those 10 numerals and then this positional significance, and that's all you need to remember to represent any number. Another benefit is that it's really compact. Right? Remember that 1,889, the year on the building. With Roman numerals, you need like 10 different numerals. With this positional number, you only need 4. And the other thing is it's kind of arithmetic friendly. Right? We've seen that in elementary school. We can easily do addition, subtraction, multiplication, division by just lining up these numbers on the rightmost position. Right? And then you can do this column by column addition, subtraction to make even large computation happen by hands. And as we may know, computer works in this binary world, but still they deal with positional numbers. Binary is just the same positional formula, but you replace the b, the base, with 2. Right? In decimal, every b is 10. In binary, every b, that's your base number, is 2. So now when we look at this number, the binary number, again, we try to parse it from right to left, starting from the smallest positional weight to some larger positional weight. And these bits would have positional weights of 1, 2, 4, 8, 16, and 32, respectively. Right? And again, we take the products between every numeral, like every bit essentially a binary digit. So every bit with the corresponding positional weight, and then add them up. That will be the magnitude represented by that binary number. So in this case, the number is 32 plus 8 plus 2 plus 1, which is 43. Right. So far, so good. Right, again, essentially the same as decimal, but we're just replacing the base with 2. All right, and there are a few terminologies I want to define right here. We're going to use them quite a bit. The kind of rightmost position, that is your least significant bit. Why is that? Well, the positional weight is the smallest. Right? Positional weight is 1. So it has the least significance compared to other bits. The leftmost position is your most significant bit. Right? Of course, it's because the positional weight is the largest. So having a 1 on the most significant bit is more significant than having a 1 on the least significant bit. Right? Just by the nature of positional weights, the weights increase as you go from right to left. All right. And you can define positional number system with any basis, going from 1 all the way to, I would say, almost infinity. It's really up to you. But here are some of the commonly referred to positional weights, specifically binary, right, base 2 that computer uses, octal, base 8, decimal, of course, in our daily life, that's decimal, and hexadecimal, which is base 16. And base 8 and base 16, they are kind of related to binary because those bases are powers of 2. And therefore, you can do sort of like a very easy conversion between binary and octal, and binary and hexadecimal, without really running complicated conversion algorithms. And many of these names have an origin in either Latin numbers or Greek numbers. So for example, septimal, base 7, right? That's septum, is 7 in Latin. And let's see, decimal, right? It's like decim in Latin. But the one thing that got me really curious is that when I was looking at this number, right, I saw like septimal, octal, nonary, and decimal over here. And they sort of correspond to September, October, November, and December. Right? But you see, septimal is base 7, but September is the 9th month of the year. Isn't it weird? Does anyone know what is happening over here? Yeah.
For the months?
For the months, yeah. Like why, September is month number 9, but it's base number 7. Or, it's number 7 in Latin numbers.
I don't know if it was Julius Caesar, but some Roman emperor wanted a couple months for himself, so he added 2.
Yeah. So at some point, like an empire in the, I think, Roman Republic, I don't know exactly the name, like he added 2 additional months. So before that, when we're at the Roman kingdom, there were only 10 months, and every month has 30 days. So every year is like about 300 days, and that's kind of problematic. After a little while, you run into some mismatch between season and months, so they eventually added 2 more months, and those 2 months are added to the front, so January and February. And January, of course, comes from the god of Janus, or like Janus, who is the god with 2 faces, signaling transition, doors. So that's the reason why there are 2 additional months, but really these come from the Latin numbers. All right. Again, with decimal, you can represent both integer parts and also decimal parts. Same goes for binary, right? You can represent integers and also decimal places. The idea is to just, continuing applying positional weights by going into some negative exponents, right? On the left part of the decimal point, we have a bunch of positive positional weights. On the right, those are still positive, but with a negative exponent, they become fractional numbers, right? So you can represent smaller numbers also using binary. Again, in decimal, we will have this 3 over here really means 3 times 0.1, right? Next 7 is really means 7 times 0.01. And the next one is 0 times 0.001, which are 10 to the power of negative 1, 10 to the power of negative 2, 10 to the negative 3, respectively. You can, of course, make similar definitions for binary. Really, they're the same positional number systems with different bases. So for a binary number, this 0 would represent 0.5, the 1 would represent 0.25, and this one is 0.125. Right? Keep dividing 1 by half, 0.5 divided by half, 0.25 divided by half, 0.125. And again, you can take the summation of all the positional weights to read out the magnitude of this number. Right? Again, 1100, that's 4 plus 8, so 12. 0.011, 0.25 plus 0.125, 0.375. So these 2 numbers are equivalent. Any questions? All right. Okay, so for small numbers, you can do this conversion quite easily. Right? The answer is for some slightly bigger numbers, how do you make the conversion happen? So if you're given this number, 135, and that could be something you type on the keyboard, but eventually it will be stored in a binary format in your computer. So at some point, base conversion has to happen. So how when you're given this number, how would you convert this to binary? I think many people may have seen this from other classes like CSE 30, CSE 25. So how would you make the base conversion? Hamza, you have some idea?
Convert like the decimal.
Yeah, the decimal to binary. So if you're given 135, how would you do the conversion?
Well, there's like 2 ways to do it. It's like the way I would normally do it.
Yeah, tell me the way you would normally do it.
I would think of the power of 2 that comes as close as possible to 135.
Yeah.
So like in that number, it's 2 to the 7 is really close to 135. So then you figure out the difference first kind of exponent you got, like 2 to the 7th. So that means like you would have like a number with like 7 positions.
Yes.
And the leftmost one would be like 1.
Yeah, representing 2 to the 7, and then for the remainder.
Ones wherever the other exponents.
Okay, got it. So let me recap what Hamza just told us. So he's saying that, well, the way that, that's also the way I like to do the base conversion is by first finding some exponents of, some powers of 2 that are very close to 135, but not quite, right? The kind of largest power of 2 that is smaller than that target number. You'll probably put down, prepare 7 positions. All right. So this is position 0, position 1, position 2. Oh. Right, prepare 7 positions, 0, 1, 2, 3, 4, 5, 6, and 7. Right, put down a 1 at this position 7, right, knowing that I already included 128 in my binary number. And they'll check for their difference. They differ by 7. So the task remaining is how to represent 7 in binary. And 7 is pretty easy to handle, 4 plus 2 plus 1. So put down 3 additional ones on position 0 and 1, 0, 1, 2 respectively. All right, that's how we like to do base conversion. Right. But you're also saying there's another algorithm. There's another way.
Yeah, there's not familiar with this one, but it's where you start with the basic buildings.
Yes.
I can't remember how it was with that.
Yeah, we're going to get to that in 1 second. So the way we like to think about it, like our brain, is starting from the largest number, right, and do a lot of comparisons. We're essentially doing some comparison between this number and all the numbers over here. That is good for our brain to handle. Like, these numbers, after you look at them for a little while, you can pretty much memorize these powers of 2. Right? But for computer algorithm, things happen in a different way. You have to think about the cost of doing this comparison and the cost of storing all these powers of 2, which is pretty high. So really, computer has a different algorithm of handling base conversion. And their algorithm is really motivated by this positional number view of a binary number. So between decimal and binary, they have the same magnitude, right? The true magnitude of the number is the same. And both of them can be represented by that formula. Positional weight multiplied by the numeral and take out the summations. And the goal is to really extract these binary numerals from that formula. So what can we do? Well, when we look at this formula, all of these binary numerals, the a n minus 1, a sub n minus 2, those are kind of already been multiplied. But you can still try to extract them out by doing some division, right? If you divide up that number by b, what will end up happening is that a0, that one is no longer a0 will show up, a0 is not a multiple of b. So if we divide up that full number by b, what we'll end up getting is that the remainder will be a0, right? The rightmost position, that is not a multiple of b. So if you divide up that whole number by b, this part is divisible by b. Right? So essentially take away b from each of those clauses, and then that is what you get as a quotient. But a0 is not divisible by b, and it will show up as a remainder. Right? It's a way to visually let that one binary bit showing up by running some division algorithm. And as you can see, this one, if you look at this new formula, this part will be divisible by b. And if you divide the whole thing by b, the a1 will show up as the remainder. For the next round. So just keep applying this division algorithm. Every time you can extract one binary bit from this magnitude. I think it's good if I show you an example. So from 135, what we'll do is we'll try to divide it by the target base to extract one bit or one digit in general from that target base. So if we do that division, first time we get a remainder of 1, and 1 would be my a0. So I'll put the 1 over here. And then I take the quotient divided by 2, I get 33 with a remainder of 1. 1 will become the second bit. Again, I just keep taking the quotient divided by 2, and then whatever I get as a remainder will be 1 bit in my binary number. When do I stop? Well, I'll stop when the quotient is 0. At that point, I know there's like no magnitude left for me to handle. And I just connect all the remainders, kind of like fold it down a little bit, right, from that direction into this direction to get the binary number. And this algorithm is kind of different from how our brain do this kind of base conversion in the intuitive way, right? So in this algorithm, we essentially recovered in this sequence from right to left, from least significant bit all the way to the most significant bit. Any questions so far? Right. And here I have an exercise for you. Again, the same number in decimal. I want you to convert that to base 3. Right? Try to apply the algorithm and see if you can make this conversion happen. I'll give you 2 minutes to work on this exercise. Right? Take out a piece of paper or on your screen. By the way, these slides, I always upload the preview version before lecture, so you can download that slide and then make some annotations. But just be cautious because I'm going to make some updates and annotations during lectures. So the final slides might be slightly different from the preview. One more minute. All right, time's up. Does anyone want to share with us their answers? Yeah. I think what's her name?
Rona.
Rona. I think Rona raises her hand first.
I got 12000.
12000. One. One. Oops. 12000. Do you get the same answer? Yeah, it is 12000. Let me just walk through this process together with you. So we start with 135. And our target base is 3, so we divide it by 3, which gives us a quotient of 45, remainder of 0. So quotient and remainder. And then 45, we just repeat this again and again. A lot of work. Yeah.
Oh, it's not showing up in there.
Oh, it's not sure. Right. Sorry. All right, and then we take 35, we repeat the same process. 3, 15, 0. 15, that's 5, gives you a 2. 5 divided by 3 is 1, remainder of 2, 1. And 1 divided by 3 would be 0 with a remainder of 1. Oh, it's 5 remainder is 0, sorry. Alright. And then essentially this will be our least significant digit, right, and the most significant digit. So you can write it out as 1, 2, 0, 0, 0. Right, and in ternary, a ternary digit, take a guess what it's called. So binary digit is bit, ternary digit would be trit. Yeah, and it's like most significant trit. Right. So far so good. And converting this number back to decimal is straightforward. You just multiply out the numerals with position weights. Right, so the way you can do it is you can write down the position weight of each position. Right, 1, 3, 9, 27, and 81. And then this number is essentially 81 plus 27 times 2 in decimal. And then that should give you 135. Right. From any base to decimal, just multiply out all the positional weights together with digit values. Decimal to other bases, we do a division algorithm. Right, so that's for the integer parts. We also have the decimal parts to handle. Right, for those numbers smaller than 1, how do you convert them to binary? And this is getting a little bit more tricky. So I'm showing here is 0.15, like a very simple decimal number. We'll convert that to binary. It's like a repeating decimal number. But we can still try to approach this conversion by looking at the positional weight formula. Right? Again, the goal is to extract some of those 8 bits for the binary representation by somehow manipulating the formula. So what can you do to extract out one of the binary bits? Right? If you want to extract out a minus 1, which is the first binary bit on the right of the decimal point, what do you think I can do with that formula? Yeah, feel free to speak up whenever you have some ideas. Anyone? Yes, Eric.
Did you multiply by 2 instead?
Yeah, you can multiply by 2. If you can multiply essentially this one by the target base, which is 2 in this case. And then if you multiply that by 2, this one will disappear, this one will become minus 1, this one will become minus 2, etc., etc. And then how do you identify a minus 1 from that new number? So a minus 1 could be either 0 or 1.
Yeah, so you keep going until you have 1.
You have 1?
And in the ones digit?
Yes. These numbers, like a minus 1, when they become a kind of term without any b products, they will show up on the integer part. Right? Show up as either 0 or 1. If it's 0, I know the first bit in my binary number is 0. If it's a 1, the first bit will be a 1. So to recap, when we multiply that full number by the target base, the a minus 1, the kind of relatively more significant bit for this decimal part, will become my integer part. It could become a 0, it could become a 1, but whenever it becomes an integer part, it's very easy to visually identify it and then put it on to your binary number. And then the remaining products, they will remain at the decimal places. So this is a way to visually separate one of the bit at these decimal places with the rest of the magnitude. So again, I'll take this example as to show you how we make these calculations. So let's say 0.15. That is my starting point. I'm trying to convert it to binary, so I multiply it by 2, which gives me 0.3. Right? What this tells me is that really a to the sub minus 1 right? That is 0. So you can write out this final binary number as 0.0. This 0 comes from the integer part of the first product. And again, you can repeat this process, 0.3 times 2, which is 0.6. And now you take out this bit and then put it as the next binary bit. Similarly, 0.6 times 2 gives you 1.2. And now I finally have a 1, which means the next bit in my binary number will be a 1. And now at this point, right, this is where things are getting a little bit tricky. That 1, I already took it out to be 1 bit in my binary number. And what I'll need for the next step is really to handle the rest of the formula, which is to only keep the decimal part 0.2 to the next step of my computation. 1 has already been included in the decimal number, so I don't have to worry about it anymore. In the next step, I'm only going to keep 0.2 and then multiply it by the target base, which is 0.4. And now, again, the integer part is a 0, so I put down a 0 in my final binary number. All right. So I'll move this binary number a little bit to the top so that I have more space at the bottom. And then next step would be 0.4 times 2, which is 0.8. So 0 goes to my binary string. And then if I do it one more time, 0.8 times 2, I have 1.6. So I need to take this number 1 to my binary number. All right, this is a lot of work, and it seems like I can never stop. All right, let's say if we try one additional step. Again, we take the fractional part, 0.6, multiply by 2. What we get is 1.2. And this is actually the same as 4 steps ahead. Right? These are the same. And by this point, I know that if I continue running this computation, I'm going to run into this repeating sequence, 0.2, 4, 8, 6, 2, 4, 8, 6. Right? And that will never terminate. And based on that observation, if I come back to my binary number, essentially I want to identify at which point things start to repeat. And that would be 0.6, right? Before 0.6, those are like two numbers coming from the original. We have now started repeating. 0.6, this is our first repeating window, the second window. Right? Therefore, you can come back to a binary number and put an overbar at this 1001 place. Right? Starting from 0.6 all the way to 0.8, those 4 bits will repeat indefinitely. Right? So now we have converted this decimal number into a repeating binary number. Right? But you see here we're running into some challenges. This number, well, let's say we're dealing with a computer system. This number needs to be stored in a fixed nice format. Right? You don't have unlimited storage resource for just a simple number like 0.15. So if we were to store this number, you're losing some accuracy. Right? And that's where many of the kind of accuracy loss, overflow issues occur, where when you're doing this space conversion and 2 bases are not fully compatible, you're losing some information. And we're going to see a solution in the coming lectures, how to maintain full accuracy when we're doing decimal to binary conversion. And here's probably a better picture of what I just did. Right? Again, multiply by 2, take out the integer part, push down the fractional parts to the next step, and then multiply by the target base. And if you're trying to convert to base 3, you're just going to multiply all of these fractional number or decimal number with 3. Right? And when you do that, you're going to have digits in the range of 0 to 2, which are exactly the range we need for ternary or base 3 numbers. So to summarize it, you can go from any base to base 10 by just taking out each numeral, multiplying by the positional weights, and then take the summation of all the non-zero positional weights. If you want to go from base 10 to some other bases, Then you need to do some different algorithms for the integer part and for the decimal and fractional parts. For the integer parts, you do division by pushing down every numeral into some remainder. For the fractional part, you do multiplication by pushing them up into the integer parts and then keeping the integer part in your final number in the target base. Right, again, any number to base 10, pretty straightforward. Base 10 to different numbers, depending on whether it's integer or fractional, you need different algorithms. And if you're given a number like, 25.3, right, with both integer parts and fractional parts, you need to separate them and then handle them differently. Yeah, any questions? Right. You see, when you interact with computer systems or digital systems in general, you see a lot of hexadecimal numbers, right? Like a very classical blue screen from Windows XP. Has anyone used Windows XP ever? Oh, what's your name? Huh?
Mark.
Mark? Yeah. When did you use Windows XP? I see. Like for some just old computers. Anyone else? Have you used Windows XP? I feel I'm old. I used Windows XP for many years. But the thing is, these numbers, when they're represented to you, like the error message, why it stops at which address is causing the problem, those numbers are represented in hexadecimal, which is base 16. And base 16 is very common because it has a direct link to binary. Right? So for base 16, you can represent numbers, let's say with 4-bit, 4-bit binary. You can represent everything from 0000 to 1111, right? Which are 0 and 15, respectively. And they fit in exactly 1 bit in base 16, or should we call it 1 digit. In base 16, you can use anything from 0 to 15, but it's also represented as a letter F. Right? When you go over 10, 10 will be your letter A, 11 letter B, 12 letter C, etc. So F is F is 15. Right? So 4 binary bits corresponds exactly to 1 digit in hexadecimal. That makes it very compact to represent even a longer binary number. Right? So this is only for compactness reason, so that you can more easily appreciate, is it at the lower parts of your memory or higher parts, roughly at which region. So essentially everything in computer, the data and the address, they operate with a binary number. So it's kind of convenient to represent them with a neighbor, a very friendly neighbor of binary, which is hexadecimal. Right. And we're actually going to do the conversion. The algorithm is different, right? It's a lot easier. You don't need to worry about addition, subtraction, multiplication, division, and anything of that sort. You simply expand every bit or every digit into more digits. We'll go from 16 to 2. So F, that is the largest hexadecimal digit, will be represented in directly 1111. Right? So the conversion happens 1 digit over here becomes 4 bit over there. Right? And the next digit, again, B is my number 11, so 1011. You can directly write down the binary representation for that 1 digit to make the conversion happen. Right? Conversion happens digit by digit. Right. I see modern computers typically use 32 or 64-bit things for both storing data and addressing the memory. Do you know why we moved from 32 to 64? Right? Like, why are we using more bits to represent data? There are many reasons. So, any ideas? When I was younger, most of my computers were 32 bits. By some point, when they reach 4 gigabytes of memory, 32 bits cannot address that big of a memory. So they have to sort of go up. And nowadays we have at least 8 gigabytes in our PCs or laptops or Macs. 64-bit is just the next power of 2, which is kind of convenient in the sense that every kind of word over here you can fit 2 of those regular 32-bit words in a 64-bit word, which makes alignment and then backward compatibility very easy to realize. I think the other reason is about accuracy. Right? The more bits you have, the more accurately you can represent a number. And that is true for both decimal numbers, as what I showed over there. That is a fixed point representation. Also, floating point numbers. You may have heard about IEEE 754, right? A different way to represent both fractional and also integers. And then with more bits, they can, of course, both have a bigger range and higher accuracy. All right. Similarly, okay, 16 is a very nice neighbor of base 2. Base 8 is also kind of friendly neighbor of base 2 because 8 is also a power of 2. So if you want to somehow convert between base 16 to base 8, instead of going through base 10 and do a lot of computation, you can go through base 2. And this not only is a lot easier, it's also less prone to accuracy losses. Again, to go from base 16 to base 2, every digit becomes 4 bits. And to convert that binary number to base 8, you essentially just need to group together every 3 bits. And this grouping happens from the least significant bit. Right? From there, we group together every 3 bits. The reason is the same. Like 3 bits can represent numbers from 0 to 7, 0, 0, 1, 1, 1, 0 to 7. And one base 8 digit can also represent 0 to 7. Right? So they have the exact same range. So therefore, every 3 bits, if you do a regrouping, can be then converted into one base 8 digit. And you see if your number, in this case, a 6-digit base 16 number, which is a 32-bit binary number, 32 is not a multiple of 8. Right? So when you are like almost reaching the end, you have to append in some additional zeros to make the conversion happen. And the 0 doesn't really change the magnitude of the number. We're thinking about like positive numbers or unsigned numbers. So feel free to append in more zeros to the left to make this into a group of 3 bits. All right. So coming back to our picture earlier, again, for this arbitrary basis, you can use division and multiplication algorithm. For those kind of bases, which are powers of the same number, right? Let's say 16 and 8, 27 and 9, right? 64 and base 4. And all of those can be converted by just grouping and ungrouping, right? Or you can also call them expansion and compression. And by going through this kind of common lower base, you can do this computation much more easily. Yeah, any questions about base conversion? All right, if not, we're going to move on to the next topic, arithmetic in binary. Binary addition is simple. It is just simple. It is strictly simpler than decimal addition. Of course, we have all learned decimal addition in the 1st and 2nd grade. Binary addition is just like a smaller addition, right? So think about it. When you learn the decimal addition, you essentially memorize the table, right? Like 10 over here, 10 over here, and all the sums of 2 decimal digits. In binary, there are only 4 different conditions you need to worry about between zeros and ones. Right? And 0, 0 is 0, 0, 1 is 1, 1, 0 is 1. Those are like the regular stuffs. 1 plus 1, well, this is too big for one binary bit to handle. Right? So you can say the sum is 1, but I'm going to generate a carry to the next bit. Right? The next bit has twice the positional weight, so I can give it a carry of 1, and for it to handle the magnitude of this larger number. Similarly, subtraction is also kind of straightforward. 0 minus 0, 1 minus 1, 1 minus 0. Right? Left is greater than right, so the result fits in 1 bit. 0 minus 1, well, 0 is smaller than 1, so you cannot really do subtraction unless you borrow some more magnitude from the next bit. And multiplication is exactly the same as the regular algebra. right? That's really because 0 and 1 are kind of like special elements over there. All right. Yeah, when I export my PowerPoint to PDF, some of these formatting issues occur. I need to eventually figure it out. So for decimal, you can do addition by lining up two numbers on their rightmost positions, and then do it bit by bit. This is such a wide classroom, it's very hard for me to reach both sides, but I'm going to try to stay here for a little while. So we're going to do decimal addition. Again, line them up on the rightmost position, and then 9 plus 5 is 4 with a carry, right? 8 plus 3 is 11, so with an additional carry, 12, so 2, and another carry, and so on. Right? Binary, exactly the same, but just following the binary addition rule. 1 plus 1, that's too big to fit in one bit, so you have a 0, and the carry out. So carry out with 1, 0, carry out 1, 1, too big, 0, carry out. 0, 0 with a carry in, which gives you a 1. And starting from this point, I think 0, 0, 0, 1, 0 gives you 1, 1, 0, 1, 0, 1, 1. And those 3 ones, you can just drop them down, and then that is the binary result. Right? Nothing more complicated than decimal. You just have to remember that you cannot represent 2. And whenever you see a 2, it has to be, generate a carry and be represented by the next bit. So here's an exercise I want you to try out with an addition example, a subtraction example, and the rules provided above. Could you try to do the binary addition and subtraction? I'll give you, again, 1.5 minutes, 2 minutes to work on this exercise. Right. Addition, people are generally comfortable with that. Subtraction is a little bit, mind twisting. So maybe it's good to have a bit of exercise. You finished?
Yeah.
How do you feel? How do you feel about the subtraction? Is it?
I don't know. I was kind of guessing. So 0 minus 1 you borrow from this one, but there's nothing to borrow. You go to this one.
Yes. Yes.
So then this is 0.
Yeah. Very nice. Michael, how do you feel about subtraction? Yeah, I'm trying to figure out how to keep track of these borrows. Right? Like, carry is kind of easy to handle. It always carries to the next bit, and then carry always goes in like this direction. Borrow, you sort of like borrow from 2 bits away sometimes, right? And people keep track of that in different ways. How did you keep track of it?
You take this one, take one from here, and then bring it over there, and then take one from here, bring it over there, and
I
2
see.
minus 1 is 1.
I see. So you're more like doing this step by step, from here to here, here to here, like only between neighbors.
Uh-huh.
Yeah. Those sound, both methods are perfectly fine. I'm going to show you how I keep track of those numbers. Because, I rarely get lost for addition examples, but for subtraction, sometimes just, too many things for my brain to handle, right? So most people have got these two examples done. All right, let's do them together. So 1 plus y is 0 with a carry of 1. 1, 1, 0, carry of 1. 1, 1, 0, carry of 1. 1, 1, 0. With like a final carry, but you can sort of like show that carry over here. With subtraction, 1, 1 gives you a 0. 0 minus 1, that's the borrow case. The way I like to keep track of it is I put down a minus 1 over here and a plus 2 over there. Right. I'm sort of converting this 0, 0 into minus 1 and 2. Like, although it's very weird, the benefit is that by putting down these numbers on top and then showing them with the corresponding sign, you will never get lost about like which one is like positive and which one you're trying to do a subtraction with. And then now coming back to this column, 2 minus 1 is 1. Negative 1 is smaller than 1, so I cannot do it. I need to borrow from the next bit, which becomes a positive 2 over here. 2 minus 1 gives you a 0. And finally, 1 minus 1 is a 0. You probably don't have to follow my method. It's just how I keep track of both the sign and the magnitude when we have this borrow chain. All right. And now let's take a look at the magnitude of these numbers. Pick a different color. So what is 1001? So that is 9, right? And then this is 7. What do I get as the result? Well, in 5 bits, it is 16. Right? In 5 bits, it is 16. But this is really a case where we call an overflow. When the result does not fit within the same bit width as your inputs. And let's say a computer, like we have 32-bit numbers, and we have like a 32-bit added. If your result cannot fit in that 32-bit, there's no way you can store it. All the registers on the memory cells, they are 32 bits wide. So when your result is longer than your input bit width, right, then you have an overflow. Right, essentially, you can also think of it as whenever we have a final carryout from the most significant bit, that indicates an overflow for these positive numbers. Okay, so in the second example, again, we have 9 minus 7, which gives you a 2, and that's perfectly good. And again, if you have a final borrow from that 4-bit number, that would indicate an overflow in unsigned subtraction. So I'm just representing it over here. When you have an extra position in your output, like wider than inputs, that's an overflow. All right. So for base conversion, we learned about integer and decimal places. For addition and subtraction, we learned about positive numbers. So I guess the next thing you should expect is negative numbers. And the most common way to represent negative integers is using a scheme called 2's complement. 2's complement. Right? It's like a pretty weird word. 2's complement. Why is it called 2's complement? All right. So this is really binary's complement. So for example, when you talk about decimal numbers, have you heard about 10's complement? No. Well, essentially, a way, if you want, you can represent decimal negative number. Instead of the additional sign, you can represent it using 10's complement. So for any base, you have this standard way of handling negation by representing negative number with some extra luggage. I will get to that in 1 second. In 2's complement, positive number is just any number starting with a 0. Right? And 0 followed by the magnitude. So number 5 is 0 followed by 101. When it has a leading 0, a 0 at the most significant bit, it is a positive number. For a negative number, okay, so let me read this sentence out. Negative n is represented by 2 to the power of small n minus n, which I know is kind of confusing. All right, so I'll help you to parse through this sentence. So n, lowercase, that is the word length, essentially the width of the number. If it's a 4-bit number, it will be 2 to the 4. And this n is the magnitude, or I should call that the absolute magnitude. Right, the absolute magnitude of that negative number. So this is really saying that, let's say if you want to represent negative 5, you need to do 2 to the 4, because negative 5, I need 4 bits, minus the absolute magnitude of the number, minus 5. And all of these, 2 to the 4 minus 5 will happen in unsigned positive binary. So you do 1, 0, 0, 0, 0, minus 0, 1, 0, 1. If I list them out in the column method, 0, 0, minus 0, 1, 0, 1, I will get 1, 1, 0, 1, and a 0. But this 0 is kind of not needed. I'm trying to fit the result within 4 bits. So 1, 0, 1, 1 is really the representation for a negative 5. The way I think about it is I think of every negative number as carrying an actual luggage of this magnitude. Right? That one is not shown. It's like an implicit luggage. But it always has to carry this additional luggage. And I think some of you have heard about this. When you want to do negation in 2's complement, you flip the number and then add 1 to it. Right? That's how by 2's complement is taught in many other classes. But what we're essentially doing over here, flip and plus 1, is really we're saying that to flip a number, we're essentially subtracting the number from 1, 1, 1, 1. Right? 1, 1, 1, 1 minus anything will be flipping that number, flipping each individual bit. But 2's complement is defined as 2 to the power of 4 rather than 2 to the power of 4 minus 1. So I need to kind of add 1 to it. Right? But this is essentially the same as 1, 0, 0, 0, 0 minus the absolute magnitude 0, 1, 0, 1. So you can think of 2's complement in multiple ways as either flip plus 1, right, which is like a rule that you just have to memorize, or in terms of the definition, it is you're subtracting that number with 2 to the n. Right? And these two are equivalent. Right? Different views, pick whichever you like. Okay? Just take a look at a few of the negative numbers. Negative 1 is this number. So if you want to interpret it as the magnitude, it would be flip 0, 0, 0, 0 plus 1, 0, 0, 0, 1. So you know the absolute magnitude is 1. So this representation is for negative 1. Right, what about negative 4? We take this, we flip it, 0, 0, 1, 1 plus 1, 0, 1, 0, 0. So the magnitude is 4, so this representation is negative 4. You can easily go from negative to positive by flipping and plus 1 to interpret the magnitude of a negative number. I want to spend one more slide on this actual luggage perspective because it's kind of important later when we want to look into multiplication algorithms and its implementation in hardware. 2's complement negative number carries an actual luggage of negative b to the n. So no matter whatever number you write, if it has a leading 1, we know it's a negative number. So the way to interpret its magnitude is by first reading out these 4 bits in unsigned and then adding that actual implicit luggage. So the very same number, 1011, its magnitude can be represented as 8 plus 2 plus 1 minus 16. So this is the actual luggage. Right? It's never shown, it's implicit, but whenever you see a leading 1 on the most significant bit, you know it's a negative number, and you need to just add in that negative number. Right? It's kind of a different perspective compared to that flipping and +1 algorithm, right? It's like a more formal positional weight look, whereas that flip and +1 is more like an algorithm, right? That you just got to memorize. Any questions so far about representing numbers, both positive and negative, in 2's complement? So far, so good. All right. So after we have seen how to represent numbers, the next task is probably do some meaningful things with these numbers. Let's see if addition and subtraction works. 2's complement addition, it just works. It simply works. You line up these 2's complement numbers, you add them up. The result, by throwing away any carryout, is the correct result. And you can verify this by enumerating different cases. The first case is positive plus positive, negative plus negative, and then negative plus positive gives you a negative. Negative plus a positive gives you a positive. Right? And these are all the scenarios you could run into. And as it turns out, if you just follow the regular binary addition rule, it just works. This is the reason why in hardware, you actually have the same arithmetic implementation, the same arithmetic circuitry for unsigned and 2's complement addition and subtraction also. Right? They can share the same hardware because they follow the same binary addition rule bit by bit. But the question is, okay, well, you can, of course, you can learn this real quick. You don't have to really spend this much time to just know it works. But the question is, why do they work? Right? Why, specifically, why we can throw away those carryouts while getting a correct result? Right? What are we actually doing over here? Any ideas? Right? In terms of that positional weight explanation, what makes it work? Actually, I'll let you think for 30 seconds, and I want you to talk with people around you and see if you can come up with some group solutions or group ideas. Yeah, no, this is not a straightforward question, right? But you see, I'm really trying to invite you to think in terms of not just bit-by-bit binary operation, but in terms of the definition, the meaning of positional weights, and those actual luggage. All right, guys. Let's get into groups of 2-3 people and then have a discussion and see what you think and what other people think. And if you can together even sharpen your ideas. And what's that? Melissa? Do you want to get together with Mark over there and then do some discussion?
Numbers get bigger, defining values get smaller. Gets smaller as the number gets larger. And it's the opposite for the positive. So basically, when they overflow.
Yeah, specifically why we can throw away these extra carryouts.
That is when the positive overwhelms the negative in that sense.
What do you think?
Because you need a larger decimal positive with a
Yeah, you see these numbers are correct in the 4-bit range. So there's really no overflow. Right? Yeah, unsigned carryout equals overflow, but in 2's complement, that's not true. Right? We can just throw away the carryout, but the result is still correct.
I don't really
and the remaining 4 bits are correct.
It's just because when you add them,
Maybe the negative overflow or something.
so like
Turns it into positive.
for the -4 and the 3, they don't overflow.
Yeah, but those two are like negative. They're negative originally, negative in 4-bit, negative in 5 bits. So it has always been negative, but still correct.
So once you pass the 0,
Any other ideas?
change signs.
doesn't overflow.
It doesn't overflow. There's no extra fit
Continues to
because
Yes.
the negative is larger than the positive.
Oh, I thought you meant the negative.
Yeah, negative and positive, they could go in both
Oh, that
negative
one-
and positive
That
direction,
one
the bottom two.
overflows as well, but when you have
And
to
still the
take
question is why can we throw it away? Yeah.
If I want to run this question,
Location.
excluding
That's true, right?
very
You can
large numbers.
you have two ones, you can
You
take
see
away
from
one.
-1 to -4.
Still asking yourself
The
why
first
you
two
can throw it
bits
away.
are ones.
Yeah, why you can truncate.
because
Wait,
So when you add them, it'll be
I think I
hard to
understand.
start with 2.
It's the only like
Well, that's the negative plus negative. Because if you had
So
-4,
the first two bits will
Not
just,
quite, because eventually we're
like,
going to see some two's complement
for the
overflow
negative and
example
negative
where we cannot always
if
throw
you
them
didn't
away.
ignore
But
it, it would
saying,
say
you know, when we do not have our
-16 plus
overflow,
8,
we
which
could
is
throw it
just
away.
-8, so you can easily
That is actually for some
ignore it.
complicated
Do you know what I
reasons.
mean? Is that why? It's just going to be like negative.
Melissa, Mark,
8
did you come up with any ideas?
-7. I don't know if
there's an extra 1. Like you're talking about -3 -4, right?
I just mean like the 1 1 0.
You sort of have an extra digit. What do you mean by having an extra
That's
digit?
-16 plus 8
Yeah.
plus 1 is -7.
You can
And it's
ignore
also -8 plus 1 is
Yeah,
negative.
sort of.
So you can ignore the
That's
first.
how we score algorithms.
Uh, You
I
just,
don't know.
Yes.
well, I don't. You just ignore it
Yeah,
because you
and
can. I guess there's no like.
But is that why? Because
Extra digit there.
it's
So do you mean we can throw it
the
away?
math is just the
Yeah,
same.
we can throw away that final carry out.
Okay.
Yeah, and the rest of the
Yeah,
remaining
I
4
guess.
bits, it
Yeah,
is the
that-
correct
that's
number,
also-
right? Based on the table, based on the decimal numbers.
Somewhat true.
So I think
But then I guess for the
case by
bottom,
case by case.
Yeah, because
not
it doesn't
very
work for the
Negative
bottom.
yeah.
But like you just ignore
Just
the
to be
first
negative.
bit because
The negative
you
number,
have
it should still be negative, yes.
because you don't go past -8 or you don't go past. You don't have an extra bit.
But I think
Yeah, still the question
we're trying
remains
to
why
figure
we're
out
throwing it away.
Mhm.
Right, we're throwing it away over here with
Um,
1 1, over here with 1
It's
0 as the
because
first 2
it's
bits.
it's still because the fourth bit you don't need to check the overflow bit. How do I explain? Like for example, if you did -5 plus -4, you get -9, and -9 doesn't.
Yeah,
You can't
that's an
represent
interesting
-9.
perspective.
So you only did -3 and -4
Yeah, I
because
think
it
that's
doesn't
a
go
valid
past
explanation.
-8.
Like again, there's no
So like if you did
correct or
-5
wrong
plus
answers,
-4,
but I think that's,
it would've
you know,
worked.
it has its validity.
That
Like
makes
we're having
sense.
the sign
And
and
then
it's like
if you look at
repetitively
that,
represented on the
so
inputs.
the largest thing you can
And,
get is -4
and,
plus
and
-4.
as
And the decimals from
Mark.
-1 to
Yeah, as Mark said,
-4.
the magnitude doesn't
It's all
really
ones.
propagate to that most increment bit, so you
And
can
when you
sort of
add 1,
like
1,
have a
and
more
1,
compact
1,
way of representing it.
the first
I
2
think
bits will always be
That's
1, 1.
that's a good explanation.
And
Alright.
you make it worse.
I don't know how to explain it. But it's
That's
almost
okay.
like intuitive.
Alright, let's get back together, and I think I'm hearing some good opinions. I want to hear from these two groups. Do you have any ideas? Good. Julie and Qingyu, any ideas? Yeah, how would you think about this? You know, this rule of being able to throw away the final carryout.
I think maybe when two negative number plus negative, this means and this will present a negative sign too. But if a negative number plus positive number, like this one, they will present a positive sign. And maybe it will be a overflow number.
Yeah, these two cases, these are like all no overflow cases. The result is valid in 4 bits. For the negative and negative case, you could say that, well, we have 2 negative numbers, and for the result, I just need to represent it as a negative number, right? And with 5 bits, has a leading 1, so it's a negative number. With 4 bits, still with a leading 1, so you can still think of it as a negative number. I think we haven't really got quite to the answer to this question, all right? Why are we able to throw it away? What makes us able to throw away that extra 1? Right? So let me hear some voices from other groups and see if we can collectively come up with some explanations. Any thoughts from this side of the class?
For the negative and the negative, since we have two ones in the front, in this case it's negative 16 and 8.
Yep.
If you add those up, it's negative 8. If you just drop the carry out, it's the leading one is still negative 8.
Yep.
So, I don't know if that's what you were asking.
Yeah, you're essentially saying that we have these two ones, right? And then throw away one of them does not affect the fact that it's a negative number.
Yeah.
Do you think you will always get two ones when you add together two negative numbers?
No, yeah, I don't know. For the 1 and the 0, that's where I'm not sure.
Yeah, for the 1 and 0, it's kind of harder to explain. All right, I'll bring you back to this actual luggage perspective. Every negative number comes with an actual luggage. And for this 4-bit number, it is negative 16. So if you think about these two negative numbers added together, right, each of them carries a negative 16. Right, 3 is not really shown as a 3, it's shown as positive 13, but there's an actual luggage of negative 16. And when you add together these two negative numbers, you have two copies of this luggage. Right, you're actually trying to subtract 32 from it, but you only need to subtract 16 from the negative result. So what you can do is you can, if you keep that leading one, you actually not subtracting enough. You need to further subtract 16 from that number to get back to only a single copy of the luggage. So essentially, you start with two copies of the luggage. The result also carries two copies, but you only need one copy. That's the reason why you can throw away 16. All right. Or if you think of it as a 5-bit number, 11001, right? In terms of positional weights, it would be 1 times 8 times 16, and the actual luggage of negative 32. If you show it as a 4-bit number, you have 1001, positional weight of 1, positional weight of 8, and the actual luggage of negative 16. And these two sequences are just equivalent. Right, negative 32 and 16 together is essentially negative 16. So that actual 1 bit does not do any help in terms of providing the necessary positional weights and the necessary luggage for the final negative number. For the bottom case, you sort of have a similar explanation. So this one carries actual luggage. This one does not. The result does not require a luggage. So sort of throw away the luggage. And that's why you can throw it away. Think of it as something that the input numbers inherently carries, and depending on how many copies you need at the output, it allows you to sometimes throw away that actual luggage, right? By throwing away the carryout. Yeah, try to work through these examples a little bit and think about the relationship between the implicit luggage and the most significant bits, and the impact of having more ones on the left to the left of a number. Or maybe for the bottom, I actually illustrate it like this. Right, negative 5 is really 11 minus 16. Right, positive 6 is just 6. And what you need at the output would be, of course, just 1. But if you add together those numbers, you have sort of like an actual 16 from the top. So, or I should say it like this. This negative 5 is like negative 5 represented with an actual 16 of its positional weight if you think of it as an unsigned number. So unsigned number that is not negative 5, it's negative 5 plus 16, right? As unsigned positive numbers. When you add them together, you should not have this extra luggage. So you throw it away. Right? You throw away exactly the position of 1, 2, 4, 8, and 16. Right? Think of everything as unsigned addition. A negative number I represented with that negative number plus the positional weights, the actual luggage. And this luggage needs to be thrown away when you get to the results. All right. I mean, don't worry too much about these abstract concepts. This is only like, some brainstorming, and let's just together appreciate the positional number systems and the actual luggage. And feel free to have some alternative perspectives. Those are perfectly fine too. All right. So for 4-bit binary number, negative number and positive number, of course, have different ranges. For unsigned numbers, they can only represent positive stuffs, and they can go from 0 to 2 to the 4 minus 1, which with 4 bits is going to be 0 to 15. Right, let's say with 4 bit, you can go from 0 up to 15. And in 2's complement, we're cutting that range in half. The lower half will be a positive number. The upper half will carry this extra luggage to bring them down to the negative range. So for 2's complement, you can go from 0 up to 7 on the positive side. And on the negative side, you can go until negative 8. Right, so it does not have a symmetric range. And the reason is to avoid having 2 zeros. Right, 0 is sitting at the center. If you want a symmetric range, you need to have both positive 0 and negative 0. 2's complement is only 1 0, so it has to be biased. And this is biased towards the negative side. And the last thing I want to show you is, when you do addition, sometimes overflow could happen. When you add together 2 numbers in 2's complement, and these are like pretty big positive numbers for 2's complement, the result does not fit in 4 bits, right? Because these 2 together, added using normal binary rule, you get like a negative looking number, and that is incorrect in the 4-bit sense. Similarly over there, right? 2 pretty negative numbers added together. If you only keep 4 bits, it's a positive number. So in this case, throwing away the actual carryout does not give you the correct result. And these are overflow situations. And overflow happens really, when you add together 2 positive numbers and you get a 4-bit negative number, right? Or you add together 2 4-bit positive number, you get a 4-bit negative number, right? Obviously, that's incorrect, and that's the only case where overflow will happen. When you add together a positive and a negative, you will never have an overflow because the result is, getting closer to 0, right? You kind of converge towards 0. So you only have to worry about overflow when 2 of your inputs are having the same sign, and the result is having a different sign from any of the 2 inputs. All right. So I have a small exercise for you to do when you get home. That is to try out 2's complement subtraction and to see if you ever get overflow. Some of these numbers, when you do the subtraction, the result will not fall within the same range. Right? In that case, you're getting a subtraction overflow. Try to find an example, like positive example, negative example, see how overflow happens in both directions, and see if you can derive some general rule to represent the overflow situation. And the next lecture, this will be our starting problem. All right, to sum it up, we talk about positional number systems, base 10, base 2, base 8, 16, all the different bases. You should be able to make conversion between them for both integer and decimal places. We talk about addition and subtraction for unsigned numbers, and that has one kind of overflow condition. Also for 2's complement numbers, which has a different set of overflow conditions. We're going to continue the discussion about negative representation of 2's complement and another scheme called 1's complement in tomorrow's lecture. Right. So that's everything for today. And don't forget to do the unbound survey if you haven't.
Mine too.
Thanks for trying to explain it.
I think you were right about the 16.
Yeah. Well, I think you were also right.
Oh, so this is
I
not
think it's
graded.
just situation.
So there's no point for this question. This is only some question for you to research and prepare for the upcoming lecture. So
Oh,
these
yeah.
questions with a point, those are only graded.
Thank you.
What is? Did you just enroll? I don't think I saw you.
Oh, I just, the date was actually yesterday.
I see.
I accidentally,
I see.
but I was enrolled.
Oh, I see. Probably just didn't notice. No, it's not for point. Yeah, it's just I said like attendance is expected but not mandatory.